Okay, well, good morning, everybody. So I'm going to be talking today about, I've slightly expanded the title that was on the program, sorry, at a moment's notice, but I'm going to be talking about rare earth elements in the copper gold uranium systems of the Eastern Fold Belt. I'm not going to venture over the West. And I'm just going to kind of give a bit of an overview of the state of the research, as well as some really preliminary results of this new GSQ-ANU collaboration that started a few months ago. So down south, myself, John Mav up the front, and Anthony and Michael are working on it. And up here, Matt, Courtney, and Vlad have been really helpful. So rare earth elements are one of these new economy minerals that everyone's talking about, which seem to be things that we reckon are going to be pretty important in the future, right? So we need things that they might not have been historically looked for. They might have just been tossed into the tailings, but we think they're probably going to be useful. So it probably makes sense to start thinking about them now. And the rare earth represent one that everyone knows about, but they're actually pretty poorly economically, especially metallurgically, slightly geologically, and very politically understood of these NEMs. Like I said, we need them for Tesla trucks, we need them for wind turbines. So let's figure out what they're doing. So even though Queensland doesn't have any operating mines for rare earths at the moment, it has very favorable geology for a number of different styles of mineralization. So we have the Proukland volcanic hosted rare earths, which I'm much more used to talking about. Then we have the two that are relevant to the Isa region. One being the heavies down in the phosphorites, which Dr. Valtich will tell us all about soon. And then the ones, the light rare earths associated with the copper gold uranium systems a bit closer to here. So there have been two resources hammered out. So one at Elaine Dorothy by Hammer, actually, and then one at Milo by GBM. The Mary Kay tailings actually probably represent one of the most significant rare earth deposits in the country, really. And I think that's a GSQ estimate, but that really stacks up against some of the other deposits out there. So along with ones that have already been identified to have resources or estimate of resources, many of the prospects and occurrences kind of crop up over the place. And these include things like Coppeny, which has recently been re-drilled on a CEI grant by Hammer, and the Brown Snake and MIM, and some stuff near SWAN, as well as lots of these deposits having sniffs of rare earths in them. So the copper gold systems in the Isa region are often classed as just IOCGs in general, but that's really a poor way of looking at it because some of these deposits are as different to each other as they are to deposits of different commodities entirely. So two types of these deposits in the area showed significant rare earth enrichments. One of these being the fluorine barium-rich IOCGs. So these are kind of your senso stricto IOCGs, your Ernest Henry, your OD, that sort of stuff. And it also includes the little E1 and Monikoff, which are all clustered next to Ernest Henry up there in the northeast of the outcropping inlier. The other class is much more diverse, and I'm just calling it copper gold uranium rare earth skarns. So it's kind of a very broad category there, but includes things like Mary Kay, Elaine Dorothy, and Coppeny, as well as potentially SWAN, which even though it sits further to the south, actually shares a lot of characteristics with these deposits in the center. And then we have things that are really understudied, but they look like they might actually be a combination of these two types of deposit, things like Milo. And I'm going to talk about all these in a little bit. There are other styles, so things like our iron sulfide copper gold and our fluorine barium poor IOCGs, which are more like these ironstone hosted IOCGs, that seem to actually be pretty rare earth poor, as Vlad was talking about earlier. I do put a few asterisks there because the amount of data out there doesn't really allow us to say conclusively whether or not they are, but it appears that they just don't have the same enrichments, which suggests that they actually are quite dissimilar to some of these other ones. And all of them, essentially without exception, except for the ones Vlad was talking about, which have a little bit of heavy rare earths in coltha and stuff, they all seem to be very light rare earth enriched. So our fluorine barium-rich ICGs, as the name suggests, they are enriched in fluorine and barium and carbonates, which are usually associated with uranium. Oh.
Just wait a second. The video somehow got turned off.
Okay.
Oh, man, you know how to change the story.
That's okay.
Okay. Follow me. Sorry about this, everyone. How do we get over? Oh, there you go.
There we go.
How that happened.
Okay, we'll keep going. I'm not starting again. So fluorine barium-rich ICGs, full of fluorine and barium with often associated uranium rare earths. They're really similar to OD in a lot of ways. The main mineralization stage is characterized by a sulfide, magnetite, carbonate, fluorite, barite, plus or minus quartz, that overprints all these often stacked alterations, and in a wide variety of textures as well. So using the new geochem gathered by GSQ recently, I've just plotted up Ernest Henry bulk rock geochem, and it's kind of small, so you might not be able to see, but total rare earth content is on the y-axis and copper is on the x-axis. And as you can see, there's a loose linear relationship there, which suggests that as that copper comes in, so does the rare earths. So the rare earths might be intimately associated with that main mineralization stage. All these deposits, when you just filter the bulk rock geochem for ore, so greater than 0.5% copper, show distinct rare earth patterns. Ernest Henry in the middle, E1 on top, and Monikoff, they all have very steeply inclined light rare earths. They'll have positive europium anomalies, and there's a slight caveat that this may be influenced by the barium. However, some preliminary work we've been working on seems like it's actually pretty kosher and there are real europium anomalies. And then generally flat and very low, so kind of 10 times chondrite, heavy rare earth values. Now this isn't working. What have you done, Rick?
No, I don't know.
Cheers. All right, I think we're on. So now our copper, gold, uranium, rare earth skarns. So these show a very wide array of copper, gold, uranium, rare earth ratios to each other, which ranges from things that are uranium and rare earth rich, like Mary Kay, through to copper rich, through to rare earth rich, and have generally very complicated paragenesis, but they generally display one or full periods of skarn development that's early, and that includes pyroxene, garnet, and earth with the uranium and the rare earth minerals. That is then overprinted by later sulfide, carbonate, and quartz, with generally no or very, very minor fluorite and barite. So distinctly different assemblages to our IOCGs. Same thing, I've got SWAN bulk rock geochem plotted down there, total rare earths on the y-axis, copper on the x-axis. There's samples that have very high rare earths, no copper. There are samples that have very high copper, no rare earths. So they're probably not related to each other. They probably didn't come in at the same copper-gold mineralization event. So these paragenetic studies were probably right. These two have distinct rare earth patterns in the bulk ore geochem, which are typified by convex light rare earths. So this is where we have a slight bend between lanthanum and samarium, are weak to moderate and negative europium anomalies. So again, distinctly different to our IOCGs, and low heavy rare earths. So Milo is kind of an interesting example that has actually been studied a little bit, particularly targeting the rare earths, whereas all these other deposits, all the research focuses on the copper gold and might just mention the rare earths as an aside. But I've just ripped some stuff directly from a thesis done by Jacob Harvey in 2014. That was never published. But essentially what it's showing is that Milo is an example where you have a copper gold rare earth skarn that is overprinted by late IOCG mineralization. So the rare earth patterns are exactly the same as the two ones I discussed before, even in the same drill hole, just in different sections. So this is potentially a really interesting example of two superimposed hydrothermal systems going over the top of each other. So what I've presented there is basically the bulk of the research that has actually been done, particularly around rare earths. So that, of course, leaves a lot of unanswered questions. So what's the exact relationship to the copper-gold mineralization? As it appears, some of it is intimately associated in these IOCGs, whereas the skarns, perhaps it's a completely different event. Maybe the rare earths are already there. It's tough to say. The spatial distribution of the rare earth enriched deposits. So all those IOCGs, they're all clustered up in that northeast corner, whereas the skarns seem to be in the central Mary Kathleen domain, with SWAN being a bit of a weird one down the bottom, but it's not really well constrained. The rare earth distribution within each deposit. So are these controlled by structures? Are these controlled by stratigraphy, as it looks at like out at Coverty? They might be. These are all kind of really unknowns. And the big one, of course, is the mineralogy, because when it comes to processing it, some things like to give up their rare earths, some things don't. And so we really need to know exactly what phases these are appearing in. We should probably have a look at this before we can make really any meaningful economic assessment. And that's what this project is aiming to do. So we started this a few months ago, and we're aiming just to generally increase the understanding of rare earth behavior and occurrences in these systems. So we're doing that by combining the actually quite limited existing bulk rock geochem and mineral chem and geochron with newly gathered mineral chem and geochron and all that sort of stuff, specifically targeting the rare earths so we can pick apart these different mineralizing events. One thing that hasn't been done that we think we can really make some strides on is dating of the allanite. So allanite is actually quite good at, to be dated. It hasn't been dated before in the Isa region, and it's everywhere. So it's going to really constrain periods of hydrothermal activity in the immediate area. So thanks to the great collection of cores and samples at GSQ, we've managed to get samples from essentially every deposit that we've identified as being rare earth enriched, which is quite a list. And what we're generally doing is we're using QEMSCAN to make beautiful maps for paragenetic studies, that sort of thing, onto SEM, onto laser for mineral and trace element geochem, as well as some geocron. And Anthony couldn't come because we didn't let him get away from the computer because he's the one crunching the numbers for the geocron. So hopefully they'll be definitely ready for next year. So a little plug for QEMSCAN, which some people might not be familiar with. Similar to TEMA, but slightly different. QEMSCAN stands for Quantitative Evaluation of Minerals by Scanning Electron Microscope. Essentially, it maps out your sample using very rapid, high-energy electron beam along a predefined raster pattern. And you can change this pattern depending on your sample. So if you've got really fine-grained stuff, you can have short steps and you can really create some beautiful images. It uses the information gathered during that sequence to convert it directly to mineral phases. So you go in with a predefined mineral phase library and you can really see some amazing stuff. And we've had a great time using it. So I'm just going to present a little quick kind of comparative study on two copper gold systems that are very, very different. And you can easily class them as copper gold, but you'd be doing yourself a disservice because the exploration models for these things are completely different. Everyone knows about them, EH and SWAN. And I've directly ripped these sentences essentially from the deposit atlas, which is being presented soon. Been very useful. But essentially what you see an early period of regional sodic to sodic calcic alteration, local potassium alteration, sometimes skarning phases forming in SWAN, and then you have a late mineralization of copper gold overprinting the entire thing. Like I talked about earlier, SWAN, you see the rare earths come in earlier, whereas Ernest Henry, you see them come in late, as I'll show you. Both of the deposits' rare earth budget are controlled by these two minerals. So there is minor rare earth carbonates, except they're probably coming from the breakdown of these primary minerals and they're not volumetrically significant. A little bit of titanite, almost no zircon, but these two are the rare earth holders. So it's a scary picture, but I'll talk you through it. So these are QEMSCAN maps of Ernest Henry. And what you can see there is essentially a very brecciated, potassically altered volcanic rock. So K feldspar is in pink on here, and you can see it forms these distinct clasts. And in between the clasts is our ore mineral assemblage. So you have things like magnetite in the dark blue here. You have chalcopyrite in gold, pyrite in yellow, with some fluorite and barite in the two different purples, and apatite. So you can see clearly from this image here that the apatite is coming in at the same time as the rest of that mineralizing phase. So when you're looking at the apatite, you're directly looking at the rare earth chemistry of the mineralizing fluids. If you extract that apatite layer, you take that sample to the laser, you can easily find all the apatites and go around and zap them. And you can see that they have very distinct rare earth chemistries, particularly denoted by stuff that's been noticed previously by Cave et al., where you have cores that are enriched in light rare earths and you have rims that are depleted. So this either means that you've got alteration of those rims at a later stage, or you're crystallizing a mineral phase that's instead taking all those light rare earths. And that's something that we found that hasn't previously been described, where you have, again, you have this host rock, which is an orthoclase altered volcanic. You have a main flooding mineralization stage of carbonate, so calcium carbonate in the yellow, magnetite and chalcopyrite, with nice euhedral alanites forming at the same time. So alanite, a rare earth rich epidote, is taking all those light rare earths that are instead of going to apatite ending up as that phase. And that's what we'd expect, because given this trend, you can see that as the mineralization happens, you're also introducing rare earths into the system. So they have to be going somewhere. So as you can see from this picture here, which is just the rare earth pattern for our alanites, very full of light rare earths, up to about 23 weight % total rare earths. And by dating this alanite, you can directly date the mineralization stage at Ernest Henry, which I don't think has been done very well yet. So SWAN, so another copper gold deposit, but as you can see, completely different mineralogy to Ernest Henry. So what you've got here is you have an early skarn, which is made up of clinopyroxene in the gray, magnetite in the blue, with nice big euhedral alanites in the pink, with some sort of epidote as well in the dark pink. Then you have these sulfides come over the top in big, nice pyrites, and a little bit of chalco in there as well. So apatite occurs in this one as the little blue blebs right in amongst the skarn material. So it's probably earlier than the main mineralization stage. If we look at the rare earth element geochem of these two minerals, with apatite on the left and alanite on the right, very distinct rare earth patterns, very significant negative europium anomalies in the apatite, with slight ones in the alanite, and lots of rare earths in the allanite, so up to 32 weight percent. So if we kind of just have a look at the two of these deposits next to each other now, they have very fundamental differences in the rare earth geochem of both the bulk ore samples, but also in the minerals. So you're not just seeing different abundance of minerals causing an apparent difference in bulk rock geochem. There are fundamental differences that are reflected in the mineralogy, which means that the fluids moving into these deposits and causing the mineralization are distinctly different. And then you have to ask the really tough questions, which what does this actually mean? Like, is this a reflection of the metal source? So for example, is one of these deposits, you're getting the rare earths that are partitioning into an exsolving fluid, or perhaps you've got a fluid moving through that's leaching rare earths as it goes. And this is what this project's aiming at. We've just started collecting the data, but soon we'll have a wide library of both bulk rock geochem and mineral geochem to really start making some inferences into how these things are forming. So we've tackled about half the deposits so far. We've been up here for the past few days collecting more samples and down at the core shed in Brizzy. So lots of more QEMSCANs, lots of laser to go, lots of geochron. We had some initial results the other day that look really promising. Low common lead concentrations, really tightly constrained ages. So hopefully we can get some good information out of this. And we'll probably be looking at finishing this early to mid next year. So should have a brand new flashy presentation for next year. Lots of acknowledgements because all the companies have been really nice providing samples and doing all that sorts of stuff. And the final pitch, if you know of any rare earth occurrences around the area that I haven't talked about today, I'd really like to have a chat about this afterwards. Because it'd be great to have a very comprehensive look at exactly what the light rare earths are doing in these systems. Thank you.
Thanks, Ross. Great job. Okay, we might leave questions for the end. I don't think there are any online, so we'll have a general critical minerals question session.
Try and fix up this.
Oh, and Rick's going to fix the video.
Take that. I think he doesn't like having what I see.
I might have to turn that camera up so I'll look at my nipples and stuff. It's fine. I didn't say anything rude.
Maybe we will take one question from the floor if we can while Rick's organising video. Hold on, if you don't mind.
Have you tried monazite as well? It's been particularly good in lots of systems that we've worked on.
So as of yet, with the deposits we've looked at, there hasn't actually been a whole lot of monazite in them. So there has been a few where you have apatite with sort of monazite-y rims on them, but nothing that looks clean enough to date or do anything on. But I suspect we will find monazite in more of these. I was actually surprised that we weren't finding more. Yeah, but allanite is by far the dominant host in most of these. Yeah.
This is a question for Ross, because we skipped the question in. With the IOCG rare earth elements, for example, apatite, monazite, xenotine, how does the circuit handle them? Do they float? Are the rare earth element minerals from the already mined sections now in the concentrate or the tailings?
I would say that most of these wouldn't float in the conventional flotation circuit. The processing guys at SMI might be able to answer this better than me, but I suspect that they wouldn't. So they'd probably end up in the tailings, and because there aren't really established methods for processing the silicates, and the phosphates even are sort of marginal, so there's really been limited research into how to actually get them out. Yeah.
Another answer to that is tune in this afternoon, because Lisette Verster, who's actually a metallurgist who specializes in flotation, is going to give a talk on flotation of rare earth element bearing minerals. So that's she's the one who's going to be able to answer that question far better than I can. But the other part of that answer is that of the whole panoply of rare earth element bearing minerals that we're talking about today, there are 3 that have been commercially produced. The rest of them are all don't concentrate enough, or we don't have a method to produce them. So it's a very good question, but it's a research question partly. But yeah.
I had a question for Ross while I'm standing up here and have a microphone. Thanks. I was interested to see the difference in the rare earth element curves of your allanites between Ernest Henry and SWAN. And your Ernest Henry basically showed 2 different populations. I think it was in the light rare earths on the left, one was high and one was low. And you mentioned something about your apatites having variable high to low rare earths between the cores and the rims. Is that a growth zonation or is it an overprinting, do you think?
So the apatite in Ernest Henry had two distinct patterns. Yeah. So the cores were enriched and the rims were depleted. So that can either be interpreted that you have something altering the rims and releasing the light rare earths, or another phase started crystallizing that was taking up all the light rare earths. And our interpretation of that is the allanite started crystallizing at that point, taking out the rare earths or taking out light rare earths, I should say. So your apatite that was growing later, so your rims didn't have any left for it. The rare earth content of the allanite varies as well, because allanite sits on the epidote solid solution. So you can be an epidote that just has a few % rare earths, or you can be all the way. And I think entirely pure allanite is something like 48% total rare earths. So you can sit really along that spectrum anywhere. And epidote's pretty happy to take up almost everything, but very much tilted towards the light rare earths.
Okay, yep. So it's growth, not an overprint. Yep.
Yeah, it's most likely growth. Yep.
Does anybody have any questions for Vlad as well on the mineral systems work that he's doing? Since we skipped that talk as well at the start of this session. Are there more questions online, Matt? All right.